Okay, so this is section 5.6, and we're looking at theorem 5.63 and theorem 5.64. I don't know if I think that's it. That gets us to the end. Now, for theorem 5.63, they're making these theorems in essence because, through their definition, I would say we can really just go with the properties of exponentials. I'm happy with that. And so, we just want to remember those properties, that if I have e to the z1 times e to the z2, that's just e to the z1 plus z2. Two, if you have e to the z1 times some e to the zn, and we had a z2 and z3 and so forth, well, that's just e to the sum of all those. So sum k equals 1 to n of z sub I. 3, e to the z is never equal to 0, and because you remember that e to the z is e to the x, e to the iy, and so this is the arg, right? This is arg e to the z, and so this is the modulus, and that is never 0. E to the x is never 0, because that's just real numbers, right? And so that's never 0, so there is no way to make that thing 0. 4, e to the z inverse, multiplicative inverse, is just e to the negative z. Now, of course, to have that, they don't have the other, they don't have a rule like e to the z to the, oh, I know why they don't. I was going to say to the w. The problem is we haven't defined, we've got e to the z, that kind of exponential, but we haven't yet defined something like z to the w, so we won't worry about that yet. 5, e to the z1 over e to the z2. You just subtract the powers, z1 minus z2. And finally 6. This is only, to me, the only real new one, and that's e to the z complement. I keep saying complement. I don't know why. Sorry, conjugate. This is e to the z conjugate. Now that one, I think you got to think about that a little bit, right? So e to the z, this conjugate idea, so I start with e to the z conjugate. Okay, that is e to the x, e to the iy conjugate. Okay, now that is e to the x, and here I really do need to go into cosine y plus I sine y. I need to go to this form to get something that actually looks like a complex number that I'm used to, conjugate of that whole thing. So then that's e to the x times cosine y minus I sine y. So now I've done the conjugate. And now that I will use a trig identity. that's the same thing as cosine of minus y, because cosine y equals cosine minus y, and plus I sine minus y. I think that's what I want. I might have to start at the other end and think about that. Yeah, that is what I want. Okay. So so then this I can write as e to the x minus iy. Oh, sorry, e to the x, well, e to the x, and then e to the minus iy. Now I can put that back together, e to the x minus iy, and that finally is e to the z conjugate. So that did take a little bit. Now, another way to see this is realizing that that's the arg. Remember that, you know, if I draw a z out this way, some other z, now we got to be careful here, e to the z and all that. But if I look at some I'll call this one w equal e to the z, okay, that's some complex number, well then w conjugate is here. So this is w conjugate. And what we can see is that if I do that, right, the modulus is the same, r is the same, r and r here, but then if that's theta, this is minus theta. And so we can kind of see that happening here because, you know, we would see that w conjugate is r e to the minus I theta. But if I write that if I write theta as y instead, right? So let's not call it theta, let's call it, you know, minus y and y. So then up here I could change that to a y. And then the r I could write as some e to the x and e to the minus iy. And so this is our e to the x minus iy, and so that is e to the z conjugate. Okay, so we can kind of see it that way from the geometry of what we know conjugates are and all that, but we can also just go through our trig identities and Euler's formula here to get it that way. But that's the only one that, you know, I think really needs something from that. And then theorem 5.64, they say if you're, you know, when you solving e to the z equals 1 has z equal 2k pi I for k any element of the integers. Now, we got a lot of z's hanging around here, but the double lines are for the integers. And so, you know, if you look at that as the arg here, right? If I say, well, e to the 2k pi I, well then, if I call that w, then arg w is anything of the form 2k pi I sorry, get rid of the I. Okay, so it's anything 2k pi. And I know that the absolute value of W is 1, okay, because I have R is just 1 out there. And so if k is the integer, in the integers, then as you look at the graphical situation here, here's 1. And if k is 0, I'm there. If k is 1, well, I went around the circle and I came back and I'm still there. Twice around. I could go around in the negative direction. So sure, that's those are all the solutions. So there are infinite number of solutions to that equation. And that brings us to the end of section 5.6.